Tonight, before you close your eyes, I want you to draw a line in space. Put it straight out from Earth, in any direction you like, at a distance of exactly 1 light year. There is nothing there. No star. No planet. No reward of any kind. Just an invisible finish line hanging in the dark. And a clock, already running. Now take the farthest ship humanity has ever flown. The one machine that is actually out there right now. Deeper into that darkness than anything we have ever built. We know its speed down to the meter per second. So do what anyone would do. Divide the distance by the speed. The answer comes out at nearly 18,000 years. And that seems to settle it. 1 light year takes 18,000 years. Question asked. Question answered. Good night. Accept that number, correct as it is, turns out to be the wrong answer. And the reason it is wrong is hiding one of the best stories in modern physics. Because tonight, there are 3 answers to this one question, and all 3 of them are true. 18,000 years, 5 years, and a little over 2 years life. 3 numbers, thousands of times apart. All correct. All describing the same finish line. By the end of tonight, you will know exactly why each one is honest. What each one quietly leaves out. And the strange, steep price the universe charges for every step down that list. So get comfortable, turn the lights down, and let the test begin. Here is the first thing worth noticing about the line we just drew. Nobody has ever raced toward it. In 70 years of spaceflight, through every rocket and every mission and every proud headline, no vehicle has ever been pointed at deep space with the simple goal of crossing distance. We went to the moon because the moon was there. We sent machines to Mars and Jupiter and Pluto because worlds were waiting at the far end. Every journey we have ever launched had a destination. And the destination did the recruiting. Our finish line recruits nobody. It sits in the emptiest kind of nothing, a point in space distinguished by no feature except its distance. And that is exactly why it makes the perfect test. Strip away the destinations, the science, the flags and the footprints, and one raw question is left standing underneath the whole enterprise of spaceflight. How fast can we actually cross the dark for real, with a clock running? So tonight, we run that test properly. 1 finish line, 1 light year out, a series of contenders, starting with machines that exist and have flown, moving through machines that were designed in complete seriousness and never built, and ending with machines that live. For now, only in the mathematics. Each contender gets its run. Each one gets an honest reading of the clock. And here is my promise about the scorekeeping. Every number I hand you tonight is real. Where a figure is an estimate, I will say so. Where a design is paper, I will say so. This channel does not do fake precision, and a question this good deserves better than that. But before any contender touches the starting line, we have to settle something bigger than it sounds. This test needs rules. Because the moment you start asking what it takes to travel 1 light year, you discover the question is quietly carrying passengers. What counts as traveling? What has to make the trip? What condition does it have to arrive in? Change those small answers, and the big answer swings by thousands of years. So before we start the clock, we have to agree on one thing. What counts as crossing that line? Start with the distance itself, because the phrase 1 light year slides past the ear so easily that it hides its own size. A light year is a length of road, never a length of time. It is the distance, a beam of light, the fastest thing that exists, covers in 1 full year of flying. written out in miles. It comes to nearly 6 trillion. A number like that refuses to mean anything on its own. So let me shrink it until it fits in your hand. Take our entire solar system. Everything you learned in school. The sun in the middle. The 8 planets. All the way out past the orbit of Pluto to the edge of the planetary neighborhood. Now shrink all of that until it fits inside a football field. The sun sits on one goal line. Pluto rolls to a stop around the far end zone. On that scale, every world humanity has ever touched or photographed up close fits inside a single stadium. And our finish line, 1 light year out, on that same scale, it sits more than 1,000 football fields away. You could walk out of the stadium, through the parking lot, across the entire city, and keep going into the next county, and you would still come up short of the line. That is 1 light year. The whole solar system is the stadium. The test is 1,000 stadiums long. And here is the part that surprises people. Even at that staggering distance, our finish line reaches nothing. The nearest star to the sun, a small red neighbor called Proxima Centauri, sits more than 4 times farther out. A full light year of travel. A journey no human machine has come remotely close to finishing. Would leave you hanging in the gap between our star and the next one. With the porch light of home shrunk to a bright dot behind you and the nearest new fire in the sky still years of road ahead, our test does not even take you to another star. It takes you 1/4 of the way to the closest one. Keep that in your pocket for the rest of the night. The line itself is enough. Now, the rules. Any honest test has them. And ours are built to catch exactly the kind of cheating that space travel numbers love to do. Rule 1. Every contender starts from home. At rest. No fair beginning, the race already moving. The clock starts at 0 speed, the way any real mission would, sitting under the pull of Earth with the whole job still ahead of it. And fair warning, later tonight, this little rule is going to embarrass one of the most famous starships ever designed. Rule 2. Every contender has to carry something, a payload, because there is a difference between traveling and simply being thrown. A bullet does not travel to its target. It is flung there, and nothing about the bullet has to survive in working order. Travel means something arrives. So each machine tonight will be weighed, and its cargo will be part of its score. Hold on to that word, cargo, because the word us is sitting inside the title of tonight's question. And before this night is over, that one small word is going to turn the entire test upside down. Rule 3. And this is the one I am going to keep folded in my pocket. There is a final rule. The expensive one. The rule that every popular answer to this question quietly ignores. I will tell you exactly why, later tonight. All you need to know is this. Somewhere out there on the track, hours from now, a ship is finally going to get fast enough to break it. And when that happens, every number on our scoreboard is going to change. That is the course. And that is the law. 1,000 stadiums of empty road. A payload that has to matter. And one rule still waiting in the dark. One more thing before the first machine rolls out. And it is the same formality every great race runs before the contenders line up. We need to send out the pace car. One runner gets to take the course first. Alone. With a perfect score guaranteed. It is the only runner in the universe that the rules cannot touch. And watching it go will teach us the first hard truth of the night. Because the flaw of this entire test, the fastest that fast can ever be, is 1 year exactly, and nothing that has ever been built or ever will be built is allowed to touch that number. Every great race begins the same way. Before the contenders line up, before a single engine fires, one car rolls out onto the track alone. The pace car. It exists to show everyone the course, to set the rhythm, to draw the line that the real racers will chase all day. So before we send a single machine toward our finish line, we are going to release the one runner in the universe that is guaranteed a perfect score. We are going to let a beam of light run the course. Watch it go. At midnight, a single pulse of light leaves Earth, aimed straight down the track. There is no countdown and no ignition, because light needs neither. The instant it exists, it is already moving at full speed. 670 million miles per hour. The fastest velocity the universe permits. It crosses the distance of the moon in about 1.25 seconds. The gap that took the Apollo astronauts 3 days. Gone in the time it takes you to blink slowly. 8.5 minutes later, it sweeps past the distance of the sun itself. A stretch of road so wide that light, the record holder, needs those 8 full minutes just to cross it. 5.5 hours in. It passes the distance of Pluto. 5.5 hours to clear everything humanity has ever explored. The entire stadium from last chapter. Goal line to end zone. Finished before dinner. And then it just keeps going. Through the following days. The following weeks. The following months. That pulse bores on through the dark, at the same perfect, unchanging speed. And the strange truth is that the journey has barely started. It spends the rest of the year, all of it, crossing the empty country between the edge of our planetary system and the line we drew. Autumn passes on Earth. Winter comes and goes. And at midnight, 1 full year after it left, the pulse crosses our finish line. The clock at the line reads 1 year, 0 days, 0 hours. A perfect run. The course record, set on the very first attempt, and never to be broken for as long as the universe stands. Why does the pace car get a score that no contender can ever touch? This is worth 2 minutes of your night, because it is the flaw under everything that follows. And the reason turns out to be almost embarrassingly simple. Light wins because light carries no mass. None at all. And in this universe, mass is the thing that speed charges for. Push on anything that weighs anything, and it resists you. Push it faster and it resists you more. Physics keeps a strict ledger on this, and the ledger says that accelerating mass costs energy. And the closer you push that mass toward the speed of light, the more brutally the price climbs. Until, at the speed of light itself, the bill becomes infinite. Every power plant on Earth, every star in the galaxy, every watt of energy in the entire universe, poured into one grain of sand, would still fail to push that grain of sand to the speed of light. Because the price of the last step is more than everything. Light never pays that bill because light never opens the account. Nothing to weigh means nothing to charge. It is born at full speed. It travels at full speed. It arrives at full speed. It does not accelerate, because it was never slow. It burns no fuel, because it has nothing to feed. It is the one traveler in existence that the rules of our test simply cannot reach, which is exactly why it makes the perfect pace car and a completely unfair competitor. And there is one more strange thing about light that I want to hand you now, quietly, and then put away. Light also keeps a very odd kind of time of its own. I am going to leave that sentence unexplained. Just hold it. The way you would hold a spare key without knowing which door it opens. At the very end of tonight, When the fastest ship of the evening finally makes its run, that key is going to unlock something remarkable. So here is where the test stands. The course is 1 light year of empty road. The pace car has finished, and the clock at the line reads exactly 1 year. That number is now the floor of this entire evening. Whatever we build, however clever we get, every answer from here forward is 1 year plus something. The whole game. The entire history of propulsion. Every engine humanity has ever dreamed of. All of it is just an argument about the size of the plus. For light, the plus is 0. For the first real contender, the machine about to roll out, the plus is a number so large that you may want to be lying down when you hear it. Which, luckily, you are. But first, one honest measurement. Before any machine touches the track, we should establish where the starting line actually is for our species. How far down this road has the human race ever gotten? The answer fits into 3 small numbers, and one of them changed just this spring. Let us measure our whole species the same way we measured the course. In light, miles flatter us. Light tells the truth. First number, the farthest any human being has ever traveled from Earth. For over half a century, that record belonged to Apollo 13, the crippled mission of April 1970, whose crew swung around the far side of the moon on the emergency path that saved their lives. 248,000 miles. A mark that outlasted the entire space shuttle era. The space stations, every astronaut of 2 generations, and then, this past April, it finally fell. 4 astronauts aboard Artemis 2, 3 Americans and a Canadian, looped around the far side of the moon and pushed the record out to about 252,000 miles. The first crew in more than 50 years to fly beyond every human who came before them. Now translate their brand new record into the currency of tonight. It comes out at about 1 1/3 light seconds. That is the updated, freshly set, current record for the human body. After 70 years of spaceflight. After 12 people walked on the moon and hundreds more circled this planet. The farthest any living heartbeat has ever been from home is a distance light crosses in less time than it took you to hear this sentence. Second number, the farthest any machine has ever traveled. That is the contender waiting in the wings right now. A 1-ton spacecraft called Voyager 1, launched in the summer of 1977 and still going. Tonight, it is roughly 16 billion miles out, and measured in light. That comes to just under 1 light day. It sits so close to that milestone that later this year, on a morning in November, already calculated down to the second, it will officially cross the 1 light day mark. The first machine in history to do so. Nearly 50 years of flying. The longest journey ever undertaken by anything built by human hands. And the odometer is about to tick over to a single day of light. Third number, the finish line, 365 light days. Put the 3 numbers in a row and look at them honestly. The human body, 1 1/3 light seconds. A record set 3 months ago. The best machine, 1 light day. A record 50 years in the making. The test, 365 light days. I am not going to dress those numbers in feelings, because they do not need any. The gap between where our bodies have gone and where the finish line waits is a factor of about 24 million. The gap between our best machine and the line is a factor of 365. We are standing in the parking lot outside the stadium, and the race is 1,000 stadiums long. And yet, here is the thing about those numbers that should put some heart back in you before the first contender rolls out. Both records moved within living memory. There are people alive tonight who were adults before any machine had left the atmosphere of this planet. And this spring they watched a crew fly farther than any human in history. One lifetime covers the whole distance from zero to here. The canyon between us and the finish line is real. And it is fast. And tonight we are going to cross it a dozen different ways on paper. But the first inch of it was crossed for real, by a machine that is still out there right now. Still flying, still faithfully doing its job in the dark. So let us stop measuring and start racing. The rules are set. The pace car is home. The course record is 1 year, and it will stand forever. Send out the first machine. The first contender needs no introduction, because you just met it in the parking lot. Voyager 1, launched from Florida in September of 1977, slung outward past Jupiter and Saturn, and now the farthest machine from Earth that has ever existed. It is the natural first runner for our test, and the fairest one too, because unlike everything else we will race tonight, Voyager is no proposal or blueprint or dream. It is out there right now, on the actual course, running the actual race. All we have to do is read its speedometer. The speedometer says 38,000 miles per hour. That is the pace Voyager has held for decades. Steady as a metronome, without burning an ounce of fuel, because out there nothing slows it down. 38,000 miles per hour. Down here, that number sounds like science fiction. It would carry you from New York to Los Angeles in under 4 minutes. It would lap the entire Earth in about 40 minutes. It is roughly 50 times the speed of a rifle bullet. And it is the fastest sustained pace any outbound machine of ours has ever managed. So, let us build the scoreboard. 4 lines. And we will keep this board running all night, updating it every time a new contender finishes a run. Vehicle, cruise speed, payload, arrival time. For our first entry, the vehicle is Voyager 1. The cruise speed is 38,000 miles per hour. The payload is 1 ton of 1970s engineering, cameras and antennas, and a gold record bolted to the side. And the arrival time, the time to cover 1 light year at that speed, comes out at 17,600 years. Say it slowly, because this is the number from the hook. The honest answer that started our whole evening. 17,600 years. Numbers that size slide off the mind. So let me hang it on the wall of human history where you can see it. Suppose a ship had left Earth 17,600 years ago, aimed at our finish line, flying at Voyager's speed. When it departed, there were no cities anywhere on this planet, no writing, no wheel, no farm. The Ice Age had not finished ending. Every pyramid, every empire, every language you have ever heard of, all of recorded civilization, from the first clay tablet to this video, would rise and flourish and pass while that ship was in flight. And only now, after all of it, would the ship be pulling up to the line. That is 1 light year at the speed of the farthest machine we have ever flown. The entire story of civilization fits inside the trip, with room to spare. And if you want the same truth told forward instead of backward, here it is. And I find this version even harder to hold. Voyager has been flying for very nearly 50 years, half a century, the longest journey in the history of our species. Measure what it has covered against our course, and the answer is less than 1/500th of a single light year. 50 years of flawless flying, and the starting line is still visible over its shoulder. On our 1,000-stadium course, Voyager has not yet made it out of the first stadium's parking spaces. No. Before anyone starts feeling sorry for the old machine, Let's be fair to it, because the truth about Voyager sets up everything that follows. Voyager was never built to run this race. It never trained for speed. Its assignment was the planets, Jupiter and Saturn, and it finished that assignment with honors. The velocity it carries was never generated by its own engines. It was a gift. Jupiter grabbed the spacecraft in 1979 and slung it onward, the way a discus thrower slings a discus. And Saturn added another throw the following year. The rockets that launched Voyager could never have reached this speed alone. The planets did the throwing. Voyager is a stone, skipped brilliantly across the solar system by the gravity of giants, and it has been coasting on those two throws for half a century. Which raises the obvious question, the one this whole test is designed to chase. If Voyager was never trying to be fast, what happens when we send out a machine that was? What is the actual speed record? What is the single fastest object human hands have ever built? That machine exists. It is flying right now. As you listen to this, its top speed is more than 11 times Voyager's. A velocity so extreme that it holds the all-time record for any human-made object. And when we feed that speed into our test, the scoreboard is going to improve by a factor of 10 in a single stroke. There is just one strange detail you should know before it takes the track. The fastest thing our species has ever built set its record on the way down. Every time it touches that speed, it is falling toward the sun. The record holder is called the Parker Solar Probe, and it may be the most counterintuitive machine in the history of spaceflight. Because we built our fastest ship ever and aimed it backward. The famous probes of the space age, the ones whose names you know, were sent outward, away from the sun, toward the planets and the dark. Parker was sent inward. Its mission is the sun itself, the atmosphere of our own star. And since its launch in 2018, it has been carving a long, looping orbit that swings it closer to the solar surface than anything has ever dared to fly. And on those closest passes, Parker does something astonishing. It reaches 430,000 miles per hour. Let that register. 430,000. Voyager, our first contender, holds 38,000. Parker's record is more than 11 times faster. At that speed you would cross from the Earth to the Moon in about half an hour. It is the absolute velocity record for anything our species has ever constructed. Verified. Official. In the books. So feed it into the test. Take 430,000 miles per hour. Hold it steady down our 1 light-year course. And the scoreboard lights up. Vehicle. Parker Solar Probe. Cruise speed. 430,000 miles per hour. Payload. About the weight of a small car. Arrival time. Roughly 1,560 years. In one stroke, the trip collapses from 17,000 years to 15 centuries. A ship leaving tonight at that pace would arrive around the year 3600. Still a monstrous stretch of time. Still dozens of human lifetimes laid end to end. But watch what just happened on the board. One better machine, and 90% of the waiting vanished. Now I have to take it back, because the number I just wrote on the scoreboard is a lie. And the way it lies is the single most common trick in every article ever written about the fastest object in history. Here is the trap. Ask where Parker hits that record speed. The answer is always the same place. At the very bottom of its dive, skimming just above the surface of the sun. That is no coincidence. And the reason lives in something you have known in your body since you were a child on a playground. Parker is never powering its way to that speed. Parker is falling. Picture a skateboarder in a half-pipe. She drops in from the lip, and gravity takes her. And, at the very bottom of the curve, she is moving faster than anywhere else on the ramp. That is her top speed. Right there at the lowest point. Now watch her roll up the far wall. She rises, and she slows, and every foot of climb takes speed away from her. Until near the top, she has given almost all of it back. The speed at the bottom was never hers to keep. It was a loan from gravity. And gravity collects on the way back up. Parker lives in that half pipe. The sun's gravity is the ramp, unimaginably deeper than any playground. And Parker's orbit is the endless drop and climb. On the way down toward the sun, it gains speed exactly like the skater dropping in. And at the bottom of the dive, closest to the star, it touches its famous record. Then its orbit carries it back up, away from the sun, and the loan comes due. It slows, and slows. And by the top of its arc, most of that spectacular velocity is simply gone, handed back to the same gravity that provided it. The record is real. Parker genuinely moves that fast, but only at the bottom of the ramp, and only for a little while. And it can never take that speed anywhere. And that is the trap in full. Suppose you tried to steal the record for our race. Suppose, at the exact moment Parker touched 430,000 miles per hour, you could somehow grab the probe and point it at our finish line, out and away from the sun. The instant it turned outward, it would be a skater trying to keep bottom of the ramp speed while climbing the wall. The sun's gravity would drag on it from behind, every mile of every day, bleeding the speed away. By the time it cleared the solar system, that record velocity would be reduced to a fraction of itself. The 1,560 years on our scoreboard assumed the probe keeps its record pace for the entire course. It cannot. Nothing can. That speed exists only in one place, at the bottom of a gravity well. And the moment you leave, you pay it back. So the scoreboard needs an honest correction. The Parker line stays, because the arithmetic is real and worth remembering, but it gets a stamp across it in red. On paper only. 1,560 years is what the record would deliver if the record were a cruising speed. It is a diving speed. And the difference between those two things is the difference between the fastest fish in the ocean and the fastest bird in the sky. The fish's record does not transfer to the air, which leaves our test in a strange and clarifying place. We have now raced the farthest machine ever flown and the fastest machine ever flown, the two crown jewels of our whole spacefaring century. And look at the board. 17,600 years. Honest. 1,560 years. On paper only. The truth is that neither of our champions was ever really running. One coasts on a 50-year-old gift from Jupiter. The other borrows from the sun and hands every mile of it back. What this race actually needs has not flown yet. It needs a machine that manufactures its own speed, owns it outright, and keeps it, mile after mile, with no giants to lean on and no gravity waiting to collect. A true engine, and the moment you sit down to design one, before you have drawn a single line, you run into the quietest villain in all of engineering. It has no force and no shape. It is a piece of arithmetic, and it has personally strangled every fast rocket humanity has ever tried to build. Let me introduce the villain properly, because it deserves the respect of a full introduction. It was discovered more than a century ago by a self-taught Russian schoolteacher named Konstantin Tsiolkovsky, a man who worked out the mathematics of spaceflight decades before anyone built a rocket. In a wooden house, mostly deaf, filling notebooks by candlelight, He found the equation that governs every rocket that would ever fly. And buried inside his equation is a trap so severe that modern engineers have given it a name that sounds like it belongs in a courtroom. They call it the tyranny of the rocket equation. I am going to skip the equation itself and show you the tyranny. And for that we need a road trip. Suppose you and I are going to drive across a desert. A big one. No gas station. No towns. Nothing. Just us. The car. And whatever we bring, the car gets decent mileage. And the tank is nowhere near enough. So we load the trunk with fuel cans. Simple. Except now the car is heavier. And a heavier car burns more fuel per mile. So those cans do not carry us as far as we calculated. Fine. We add more cans. But the new cans add more weight, which burns more fuel, which demands more cans. Do you feel the floor tilting? Every can we add to carry the last cans needs cans of its own. We are no longer packing fuel to move the car. We are packing fuel to move the fuel. For a reasonable desert, this spiral settles down, and you can make the trip, but keep stretching the desert, and something ugly happens. The fuel starts crowding out everything else. The back seats go, replaced by cans. The passenger seat goes, and past a certain point you reach the absurd endgame, a vehicle that is one enormous rolling fuel tank, hauling thousands of gallons across the desert in order to deliver. At the far end, a single bottle of water. The cargo did not shrink because you packed badly. It shrank because the arithmetic of carrying your own energy turns vicious with distance. And past a certain line, it turns impossible. That is the tyranny. And every rocket ever launched has lived inside it. This is why the mighty Saturn V stood over 360 feet tall, weighed 6.5 million pounds at liftoff, and delivered to the surface of the moon a cargo of 2 men and a buggy. This is why rockets are almost entirely fuel by weight. Thin metal skins stretched around propellant. The machines are magnificently designed, and they are magnificently designed against a piece of arithmetic that gives almost nothing back. Now feel what that arithmetic says about our race. Because this is where the desert becomes the whole story. Chemical fuel, the kind every rocket burns, carries only so much energy per pound. That fixed richness sets a harsh ceiling on the speed any chemical rocket can ever reach, no matter its size. And the tyranny is exponential, which means the punishment for wanting more speed multiplies instead of adding. Want to double your final speed? The fuel bill does far worse than double. Want 10 times the speed the rocket required? Stops being engineering and becomes typing. A number with so many zeros it loses all meaning. Run tonight's actual requirement through that machine and watch it break. Suppose we want a chemical rocket to reach just 1% of the speed of light. The modest little threshold we will meet in a moment. The mass of fuel required for a single ton of cargo comes out beyond astronomical. A rocket the size of a mountain fails. The size of the moon fails. You can hand the tyranny a fuel tank the size of the entire observable universe. Every galaxy converted to propellant, and chemistry still will not push 1 ton of payload to 1% of light speed. That sentence sounds like exaggeration. It is just the equation, doing what exponentials do. Chemistry is not underpowered. Chemistry is disqualified. Over the years, engineers have tried to slip past the tyranny rather than fight it. And I want to tell you about the most beautiful of those attempts, because its failure teaches the lesson perfectly. In 1960, a physicist named Robert Bussard proposed a ship with no fuel tanks at all. His logic was gorgeous. Space holds a thin haze of hydrogen, and hydrogen is fuel. So build a ship with an enormous funnel, a magnetic scoop hundreds of miles wide, and let it gather its fuel as it flies, the way a whale gathers krill with its mouth open. No tanks, no Tyranny. A ship that eats the road. The Bussard ramjet became the darling of a generation of physicists and science fiction writers. And for decades, it looked like the loophole. Then researchers did the detailed accounting and found the flaw. And the flaw still stings. Scooping the hydrogen slows you down. Every atom the funnel catches has to be swept up and accelerated to the ship's own speed. And that costs momentum, exactly the way a whale's open mouth drags against the sea. Run the full numbers, and the drag on the great funnel exceeds the thrust its fuel provides. The faster the ship flies, the harder the scoop holds it back. The mouth costs more than the meal. The net was heavier than the fish. So the loophole closed, and the honest conclusion stands. Carrying chemical fuel cannot win this race, and gathering fuel along the road cannot win it either. If we want a real contender, the energy itself has to change. We need fire from a deeper shelf, fuel 1,000,000 times richer per pound, the kind of energy that lives past the edge of chemistry. It lives in the atom. By the way, if this test has its hooks in you the way it has them in me, a like and a subscribe genuinely help this channel keep making long nights like this one. And this is a natural moment for it, because everything familiar ends here. Every machine we have raced so far was real. From this point forward, we race the machines that were designed in complete seriousness, by serious people, and never allowed to fly. And the first of them is the strangest project the United States government ever stamped secret. A ship designed in America, at the height of the space race, by some of the most brilliant physicists alive. Its fuel came in crates, and its engine, I am not exaggerating, was a supply of atomic bombs. In the summer of 1958, in a quiet office in San Diego, a small team of physicists began designing a spaceship that sounds, on first hearing, like a prank. The project was called Orion, and the idea was this: build a ship the size of an office building. At the bottom, mount a massive steel plate on giant shock absorbers. Then, to make the ship go, drop an atomic bomb out the back. Let it fall behind the plate, and detonate it. The blast slams into the plate. The shock absorbers swallow the kick, and the whole ship lurches forward. Then you drop another bomb, and another. Boom, after boom, after boom, thousands of times, riding a chain of nuclear explosions into the sky and out of it. Your instinct right now is that this cannot possibly work. So, let me tell you who thought otherwise. The project was driven by Ted Taylor, one of the most gifted bomb designers in American history. And its lead theorist was Freeman Dyson, one of the great physicists of his century, a man whose name is all over modern science. Neither of them treated Orion as a stunt. They and their team spent 7 years on it, funded by the United States government. And they worked out everything: the bomb yields, the plates cooling, the timing of the drops, one small bomb, roughly every second during ascent. They even flew a working scale model, a little test craft called Hot Rod, boosted off the ground by a stack of conventional explosive charges. And it flew beautifully. And you can watch the footage today. The physics checked out at every step they could test. Dyson believed in it completely. He talked about reaching Saturn by 1970. And he meant it. And given what was on his drawing board, it was never a crazy thing to say. Because here is what the crates of bombs buy you. And why Orion belongs in our race. Remember the tyranny. Chemical fuel is disqualified because it is too dilute. Too little energy per pound. Nuclear energy is a different animal entirely. Pound for pound. The energy locked in atomic nuclei runs about 1,000,000 times richer than the energy in molecules of fuel. 1,000,000. The tyranny's arithmetic still applies. The spiral of fuel carrying fuel never goes away. But feed the equation fuel 1,000,000 times richer, and the walls move back enormously. Speeds that chemistry could never touch with a universe of propellant come suddenly, almost casually, into reach. The serious interstellar versions of Orion, the ones Dyson himself published calculations for, worked out to cruising speeds in the range of 1 to 3% of the speed of light. So let us take the invitation. Tonight, the 1% Club opens its doors, and Orion is the first machine in history with a credible claim to membership. Run it down the course. 1% of the speed of light is about 67 million miles per hour. Read that against everything we have raced. Voyager holds 38,000. Parker touched 430,000. Downhill. On a lawn. 1% of light speed is 150 times faster than the all-time record of the entire space age. And on our scoreboard it works a miracle. Vehicle. Project Orion. Cruise speed. 1% of light. Payload. And savor this. Thousands of tons. Whole cruise. Cargo holds. A building in flight. Because when your fuel is 1,000,000 times richer, you can finally afford to carry things again. Arrival time. 100 years. Look at what just happened to the clock of this race. 17,600 years. Then, 15 centuries. On paper. Now 100 years. The trip just fell out of geological time and landed inside human history. 100 years is the span between the Wright brothers and the smartphone. It is long. It is still longer than a life. A ship launched tonight arrives with its grandchildren at the controls. And I will spend exactly 1 sentence on the robot alternative. A machine built to last a century could simply sleep the whole way. But do not let any of that dull the shock of the number itself. For the first time all night, the answer to our question fits inside the story of people. So why is there no Orion? Why did the most promising spaceship of the 20th century never fly? The physics never failed. What failed was everything wrapped around the physics. And it started with what the fuel actually was. You cannot test this ship quietly. Every launch is a parade of atmospheric nuclear detonations. Radioactive fallout drifting down on the very planet you are leaving. Through the early 60s, that problem grew heavier and heavier. And in 1963, it turned final. The United States, the Soviet Union, and Great Britain signed the Partial Test Ban Treaty, outlawing nuclear explosions in the atmosphere and in space. The treaty was written to stop weapons tests, and it caught a spaceship in the same net. Testing became impossible. Political support evaporated. The money dried up, and the project shut down in 1965. Dyson carried the disappointment for the rest of his long life. Orion was never disproven. It was orphaned by a law that was almost certainly right to exist. So the scoreboard keeps the entry, with an honest note in the margin. 100 years. Price of admission. 4,000 atomic bombs and a treaty nobody should want broken. That is the deal the atom offered. And civilization, probably wisely, declined it. But the century mark had been sighted, And now the question sharpens beautifully. 100 years still leaves the trip longer than a lifetime, and the ship itself was orphaned at birth. To cut the next zero off the clock, to pull 1 light-year inside a single human life, we need 10% of light speed, 10 times Orion's pace, and we need it without detonating anything over anyone's home. There is a fire like that. It is cleaner than splitting atoms and vastly stronger. The same reaction that powers the sun itself. In the 1970s, a small band of engineers in London decided to find out, rigorously and honestly, whether that fire could be built into a starship. They gave their ship a name from Greek myth, and what they produced remains. Half a century later, the most complete and most serious starship design the human race has ever put on paper. The story goes like this. In 1973, a group of engineers and scientists from the British Interplanetary Society began meeting after hours, often at a London pub called the Mason's Arms, to answer one question with complete seriousness. Could the human race, using physics already understood, design a ship capable of reaching another star, not a sketch, not a magazine cover, a real engineering study, with every system specified, every number checked, every problem faced or honestly flagged? They worked on their own time, evenings and weekends, for 5 years. 13 core members, notebooks open on pub tables, quietly designing the most ambitious machine in human history, while the rest of the city walked past the windows. They called the ship Daedalus, after the craftsman of Greek myth who built wings and flew. And when the study was published in 1978, it landed on the world's desks as something no one had ever seen before. A complete starship, 200 pages of rigorous engineering. To this day, half a century later, it remains the most detailed interstellar spacecraft design ever produced. And nearly every serious starship study since has started by citing it. Here is the machine they drew. Daedalus is enormous. 54,000 tons at departure, roughly the tonnage of an ocean liner, assembled in orbit because nothing that size could ever lift off a planet. Its engine burns the deepest fire we know. Fusion, the same reaction that powers the sun, the joining of light atoms into heavier ones, releasing energy far beyond even the atom splitting that drove Orion. And the way Daedalus burns it is glorious. In the engine's reaction chamber, tiny pellets of fusion fuel are dropped into place. 250 pellets every second, and each one is struck from all sides by a battery of electron beams, crushing it to ignition. Each pellet becomes a miniature fusion explosion, a tiny star born and dead in a flash, and a magnetic field catches the blast and hurls it backward. 250 heartbeats of starfire every second, day and night, for years on end. Orion rode a chain of bombs, one thunderclap at a time. Daedalus rides a continuous purr of miniature suns. Burn that engine long enough, and the ship climbs to a cruising speed of 12% of the speed of light. 12%, 80 million miles per hour. At that pace, 1 light-year takes about 8.3 years, and the scoreboard is ready to celebrate. But hold the applause for one moment, because this is exactly where our test earns its keep. Back in Chapter 2 I wrote Rule 1. Every contender starts from home, at rest. And I warned you that this little rule would eventually embarrass one of the most famous starships ever designed. This is that moment. Daedalus does not step onto the course at 12% of light. It has to build that speed with its own engine, pellet by pellet, and its own designers published the schedule. The burn takes nearly 4 years. 4 years of continuous fusion fire before the ship even reaches cruising pace. Fold the acceleration honestly into a 1 light-year run that starts from rest. And the true time comes out close to a decade. So the board gets its most honest entry yet. Written in 2 lines. Voyager. Daedalus. Cruise speed. 12% of light. Payload. 450 tons of instruments. A scientific cargo heavier than the entire International Space Station. Arrival time. 8.3 years at cruise. And call it 10 from a standing start. By the ship's own published numbers. Either way, the 10-year line has been reached. Stop and feel this one. Because we have crossed a border tonight. 1 light-year in about a decade. A journey you could follow, start to finish. Inside one stretch of a single human life. You could watch this ship leave on your 40th birthday and see it arrive by your 50th. All night, the clock has been falling. 17,000 years. 15 centuries. 100 years. And now 10. For the first time since the pace car left. The answer to our question sounds like something a person could simply live through. Now for the rest of the honesty. And with Daedalus, the honesty comes straight from its own designers. Which is exactly why this study earned the reputation it has. The engineers found one problem they could not engineer around. And rather than bury it in a footnote, they printed it. The fuel. The pellets that feed that magnificent engine are built around a rare substance called helium-3. And helium-3 has an inconvenient address. There is almost none of it on Earth. Trace amounts. Nowhere near the tens of thousands of tons Daedalus burns. But there is a place in the solar system where it exists in abundance. The atmosphere of Jupiter. And so the study says, plainly and without blinking, that before this ship can fly, humanity must first build a mining industry at Jupiter. Fleets of robotic factories drifting in Jovian clouds, harvesting fuel for 20 years, and hauling it back across 500 million miles to fill the tanks. Sit with the shape of that for a second. The ship is designed. The physics is sound. The engineering is written down to the bolt. And the fuel gauge sits on empty until we industrialize another planet. A perfect blueprint. Waiting on a gas station that does not exist. The pub engineers proved that a 10-year light-year breaks no law of physics. And in the same breath they showed what it costs. The price is an entire civilization's worth of infrastructure. Purchased in advance. And notice something else. Something quieter. Because it is about to become the whole story. Look at the pattern forming across our scoreboard. Every time the arrival time falls, the machinery behind it swells. A 100-year trip wanted 4,000 bombs. A 10-year trip wants an ocean liner of star fuel and a mining colony at Jupiter. The clock shrinks, and the bill grows. And the bill is growing faster than the clock is shrinking. Hold that pattern. Later tonight it gets a name. But first, one more door. Because there is a question sitting in the wreckage of every design we have raced so far. And someone finally asked it out loud. Orion carries bombs. Daedalus carries 50,000 tons of pellets. Every ship all night has been strangled. One way or another. By the same old spiral. Fuel hauling, fuel hauling, fuel hauling. Tsiolkovsky's Tyranny. Still collecting after a century. So here is the question. What if the ship carried no fuel at all? We watched the scoop fail. So forget gathering it along the road. What if the engine, the tanks, the entire power plant simply stayed home? What if you could stand on Earth and push? That question has an answer. It was announced in New York City in 2016. in front of the world's cameras, by a Silicon Valley billionaire, and, seated beside him, the most famous physicist alive. The answer cuts our travel time in half again, and it carries, and I need you to hear this number now so it can detonate properly later, a payload of 1 gram. On the 12th of April, 2016, on the observation deck of a Manhattan skyscraper, the entrepreneur Yuri Milner stepped to a podium to announce a $100 million research program called Breakthrough Starshot. Beside him, in his wheelchair, sat Stephen Hawking. The date was chosen with care. 55 years to the day since Yuri Gagarin became the first human in space. And what they announced that morning was the first officially funded attempt in history to design a probe that could reach another star within a single human generation. Hawking, speaking through his synthesizer to the cameras, put the ambition in one line. Today we commit to this next great leap into the cosmos, because we are human, and our nature is to fly. There is something worth pausing on in that scene. Hawking spent most of his life in a body that could not move, and he spent that life thinking farther and faster than almost anyone who has ever lived. Of course, this project found him, the man who could not walk across a room, signing his name to the fastest voyage ever seriously proposed. Here is the idea, and its beauty is that it solves the oldest problem of the night by refusing to play. Every contender so far has been devoured by the same spiral. Fuel hauling fuel. Starshot's answer is simple and radical. Leave the engine on Earth. The design has 2 halves. The first half is the ship, if you can call it that. Engineers call it a starship, and it is a single wafer of electronics about the size of a postage stamp, carrying cameras, processors, sensors, a tiny transmitter, and a light source for signaling home. Its mass is measured in grams. 1 gram, give or take. For the chip itself, attached to it is a light sail, a sheet of material thinner than a soap bubble, a few meters across, engineered to be almost perfectly reflective and almost perfectly weightless. The second half stays on the ground, and the second half is the monster, a phased array of lasers, spread across a square kilometer of high desert, most likely in Chile, combining into a single coherent beam with a power of 100 gigawatts. 100 gigawatts is the output of roughly 100 full-sized power plants, gathered into one spotlight. And when that spotlight snaps onto the little sail high overhead, the sail is built to reflect rather than burn. And every reflected photon delivers a push. Light, it turns out, presses on the things it strikes, gently, almost immeasurably, gently, which is why a payload of grams is the entire point. Feathers feel a breeze that boulders never notice. Now watch the launch, because nothing in our race looks anything like it. The chip and its sail are lofted to high altitude by a conventional rocket. Released. And then the beam fires. For the next several minutes, the sail rides a column of light, accelerating at thousands of times the force of Earth's gravity. A violence no living passenger could survive for a second. And the chip is fine, because a wafer has no bones to break, no blood to pool, no lungs to crush. In those few minutes, the little craft passes the distance of the moon. By the time the beam releases it, coasting, silent, its engine left glowing on a mountaintop behind it. The chip is traveling at 20% of the speed of light. 20%, 1/5 of the pace car, 134 million miles per hour. Numbers this large stop meaning anything. So here is one that still means something. At that speed, The entire distance Voyager 1 has fought for since 1977, 50 years of flying, the whole first light day, is covered in 5 days. Put it on the board and watch the board struggle. Vehicle, Starship, cruise speed, 20% of light, payload, 1 gram, arrival time at our finish line, 5 years. And yes, this one keeps its number even under Rule 1, because its entire acceleration lasts minutes. The standing start costs it nothing. 5 years. A ship launched tonight crosses our line before the next presidential term ends. 60 years of spaceflight put our best machine 1 light day from home. And this design, on paper, does a light year inside an election cycle. It is the single largest leap on our scoreboard all night. And it was purchased with one honest, brilliant trick. The Tyranny taxes the fuel you carry. So carry none. Leave the engine home. Ship nothing but the message. The fine print, as always, on this channel. Before we go further, Starshot is a research program, a proof of concept, and its own scientists keep a public list of the problems still unsolved. The sail must survive the beam without a single flaw. Because at these energies, one microscopic imperfection absorbs enough heat to vaporize the craft. The 100-gigawatt array has never been built and must hold its beams steady through Earth's shimmering atmosphere onto a target meters wide and thousands of miles away. And a 1-gram transmitter must somehow whisper its findings home across distances that swallow starlight. None of these are known to be impossible. All of them are unsolved. The 5 years on our board is real arithmetic, resting on engineering that has not happened yet. That is the honest label. And wearing that label, it is still the most astonishing number of the night. So there it is. The scoreboard reads 5 years. And the room wants to celebrate. And something is stopping you. You already know what it is. You heard it before the chapter began. And it has been sitting there quietly through every gorgeous detail of the launch. Look at the payload row. 1 gram. A paperclip. A Ryzen. The little machine that crosses our finish line in 5 years carries less mass than the button on your coat. And the question this whole night is built on was never how long it would take a machine to travel 1 light year. Read the title again. The question is how long it would take us. A gram is nowhere close to us, and the moment you try to make it us, the moment you ask this beautiful trick to carry a heartbeat instead of a chip, the whole architecture comes apart in your hands. That is the next chapter, and it is the hinge of the entire night. At the start of tonight, when we wrote the rules of this test, I asked you to hold on to one small word. The word was us. I told you it would come back, and that when it did, it would turn the whole test upside down. This is that moment. The scoreboard says 5 years, and the 5 years is real arithmetic, and it belongs to a passenger the size of a postage stamp. So we have to do the thing the headlines never do. We have to take the word us seriously. Put an actual human being on the scale, and watch what happens to the most beautiful number of the night. Start with the body itself. A single adult human runs about 70,000 grams. Not 70, 70,000. Before we pack a single sandwich, before we add so much as a seatbelt, the passenger alone outweighs the Starship by a factor of 70,000. If the chip is a raisin, the passenger is a grand piano, and the passenger is only where the trouble begins. Because a human being, unlike a wafer of silicon, never travels alone. A chip in the void needs nothing. It does not breathe. It does not eat. It does not get cold. It does not mind the radiation, and it does not care whether it ever comes home. A person needs everything. Watch the shopping list assemble itself, item by item, each one dragging the next through the door. The passenger needs air, which means a sealed cabin, which means walls strong enough to hold pressure against a perfect vacuum for years. The cabin needs heat, and power, and machinery to scrub carbon dioxide out of every breath. The passenger needs water, roughly a ton per year, even with aggressive recycling. And the recycling machines themselves weigh more than the water. Food, another ton or so per year. Or else a greenhouse, which is heavier still. The radiation out there, which the chip shrugged off, will slowly shred human cells. So the cabin needs shielding, and effective shielding gets measured in tons per square meter of hull. Every one of those systems can fail, so everyone needs a backup. And the backups need backups, because there is no rescue, no resupply, and no pulling over. 1 light year from the nearest tow truck. Add it honestly, and the shape of the answer is clear even before the details are settled. Depending on the crew, the recycling, the shielding, and the margins of safety. Engineers who study long missions land a crude interstellar vehicle somewhere between hundreds of tons and many thousands. Say it in tonight's currency. The payload did not grow from 1 gram to 2 grams, or 10, or 1,000. It grew from 1 gram to something like 1 billion grams. The word us, spoken out loud, multiplied the cargo by a factor of 1 billion. Now here is the part that genuinely hurts. The reason this chapter is the hinge of the night. Your instinct says, fine. Scale it up. The laser pushed 1 gram to 20% of light speed. So build a bigger laser and push harder. 1 billion times the payload. 1 billion times the beam. Brutal. But just arithmetic. Right. And the painful truth is that this is the kind of arithmetic that arithmetic cannot survive. The beam was already 100 gigawatts. Roughly 100 power plants focused into a single spotlight. Straining the edge of the possible to move a raisin. Multiply by 1 billion, and you are asking for a beam that outshines the entire electrical output of human civilization, not by a factor of 10 or 100, but by many millions. You are no longer describing a machine on a mountaintop in Chile. You are describing hardware on the scale of a small star, aimed at the back of one ship. And even that fantasy quietly assumes a sail the size of a country that somehow stays flawless under a light fierce enough to boil continents. Do you see what the trick really was? Now Starshot never beat the Tyranny. Nothing beats the Tyranny. Starshot ducked under it, through a door exactly 1 gram wide. The whole miracle worked because the cargo was nearly nothing. A feather on a fire hose of light. Feathers ride the breeze. Pianos do not. The door is real. The door is open, and we cannot fit through it. The 5 years on the scoreboard is a genuine number for a machine, and an honest stamp goes beside it now. Because 5 years may be an answer for a chip. It is not yet an answer for a heartbeat. So the board gets its correction, and the night arrives at its true question. The one that was hiding inside the title all along. We are done asking how fast a thing can go. The real question, the human question, is different and harder. What does it cost to make heavy things move fast? Why does the universe seem to fight harder and harder as the cargo grows and the speed climbs? Is that just engineering being stubborn? A problem for cleverer machines and richer civilizations. It runs deeper than engineering. There is a bill printed inside speed itself, written into the same physics that runs the stars. and it does not care how clever we are. And it cannot be docked, because it is never charged for the fuel or the engine or the sail. It is charged for the motion. Time to read that bill out loud. Every chapter tonight has asked some version of the same question. How do we make the ship go fast, better fuel, bigger engine, borrowed gravity, a beam from a mountaintop, machine questions? All of them. This chapter asks something colder, and I promise it is the most important 2 minutes of the night. Forget how the ship gets fast. Ask what a fast ship is. Ask what it contains. Because a moving object carries something inside it. Invisible, silent, and absolutely real. And physics has kept perfect books on it for 400 years. It is called kinetic energy, the energy of motion itself. And the faster you go, the more of it you are. You already know this in your bones, even if no one ever wrote it down for you. A baseball tossed underhand. You catch bare-handed. The same baseball at highway speed breaks your windshield. The same baseball at rifle speed goes through the door of a car. The ball never changed. Same leather. Same weight. Same stitching. The only thing that changed was speed. And yet the ball at rifle speed is a fundamentally more dangerous object, because speed is a cargo. Something an object carries, and the carrying charge climbs brutally. Kinetic energy grows with the square of velocity. Double the speed. 4 times the energy. 10 times the speed. 100 times the energy. The curve climbs like a wall. So let us do the one calculation this chapter exists for. Take a single kilogram, 1 bag of sugar, and bring it to 10% of the speed of light, the cruising pace of Daedalus. Ask the books what that kilogram now contains. The answer comes out at about 450 trillion joules. That number means nothing yet. So let me exchange it into a currency the 20th century taught everyone to understand. The bomb that destroyed Hiroshima released roughly 60 trillion joules. Divided out. 1 kilogram of anything. Sugar. Water. Aluminum. Cargo. Moving at 10% of light speed. Carries the energy of 7 Hiroshima bombs. A bag of sugar. Carrying 7 Hiroshimas. Purely because of how fast it is going. Now open the ledger on an actual ship. Daedalus, at its 450-ton payload, is 450,000 of those kilograms. Multiply through and the cargo alone. Just the science package. No engine. No fuel. No structure. Carries the energy of millions of Hiroshima bombs. A crude ship in the thousands of tons carries tens of millions. And every joule of it had to come from somewhere. Nothing rides for free. Some engine. Some beam. Some burning tank had to generate that ocean of energy and press it into the ship. Joule by joule. Before the ship could be called fast. This is the bill, hiding inside speed. And notice the wording on it. Because it is the coldest line in physics. The bill is never charged for the engine. It is charged for the motion. Change the technology all you like. Fission. Fusion. Lasers. Magic. The price of being a heavy thing at 1/10 of light speed is fixed by the universe. Printed on the object itself, and no cleverness anywhere touches it. And paying it is actually 4 separate problems wearing one coat. A distinction almost every popular treatment of this subject skips. Hearing the total and shrugging is easy. Humanity has plenty of energy. The sun throws away more every second than these numbers need. True. Also beside the point. First you must possess the energy in total. And we have seen the totals. oceans of it. Second, you must generate it, convert it into a usable stream. And our entire civilization's output would need years of undivided dedication to fill one crewed ship's account. Third, you must deliver it. Actually, get it into the moving vehicle, through an engine or a beam. And every delivery method we have met tonight taxes the shipment mercilessly. Tyranny on one side, a door 1 gram wide on the other. And fourth, the quiet killer. You must deliver it without destroying the ship, because an energy flow that size does not pour gently. And a vessel drinking from that fire hose is a vessel being asked to survive its own refueling. 4 walls, 1 bill, and every contender tonight has died on one of them. Before we close the ledger, one short detour, because there is a fuel that answers the second wall perfectly, and its story tells you everything about where we actually stand. Antimatter, the mirror twin of ordinary matter, and the richest energy source physics permits. Because when matter meets antimatter, both vanish entirely, converted to pure energy at 100% efficiency. No ash, no waste. The perfect fuel, the absolute ceiling of what a fuel tank can be. It is real. We make it in particle accelerators today. And here is the punchline, delivered exactly as the accountants would deliver it. All of humanity's production of antimatter, every laboratory on Earth, running flat out for a full year, yields enough to boil a kettle of water. 1 kettle, 1 cup of tea per civilization per year. The perfect fuel exists. And at our current pace, filling a starship's tank would take longer than the age of the universe. So much for the perfect fuel. That is the bill. Then, speed is expensive in a way that is written into the universe. The price squares as you climb. And a heavy, fast thing is a rolling stockpile of bomb-grade energy, no matter how gently it was accelerated. You would think that is the worst news the cosmos could hand a starship. There is worse. And the worst news is stranger. Everything we have calculated so far assumed the road itself is free. Empty space. The one thing this journey seemed to have going for it. A vacuum. A clean track. No weather. And here is what the vacuum has been hiding all night. At the speeds we are now discussing, empty space stops being empty. The road itself wakes up, and it meets the ship head-on, at the bow. At millions of miles per hour. If you have spent any time with this channel, you have heard me say that interstellar space is the emptiest emptiness there is. About 1 atom per cubic centimeter. A vacuum so pure that the finest laboratory chambers on Earth look crowded beside it. A machine like Voyager can coast through that nothing for 1 million years and barely collect a scratch. I have said all of that before, and every word of it is true. Tonight I have to tell you the other half. That beautiful safety, the harmlessness of the emptiness, was never really a fact about space. It was a fact about speed. Empty is a property of how fast you are driving, and at the speeds our test has now reached. The same gentle nothing that has protected Voyager for 50 years turns around and meets the ship head-on. Atom be atom. At the bow. Here is the physics of it. And it is nothing new. It is the baseball from last chapter wearing a different uniform. Collisions run on relative speed. It matters not one bit whether the ball flies at the window or the window flies at the ball. The glass breaks the same either way. So take a single hydrogen atom, drifting in the void, minding the same business it has minded for 1 billion years. To Voyager, plowing past at 38,000 miles per hour. That atom is a whisper of a tap, whether too faint to measure, now drive past the same atom at 20% of the speed of light. From the ship's point of view, the atom is an incoming particle at 20% of light speed. And physics has a name for matter arriving at that energy. Radiation. Hard radiation. The kind produced by particle accelerators and dying stars. One atom is still just one atom, but you are never going to meet just one. Run the count, because the count is where the quiet turns loud. One atom per cubic centimeter sounds like solitude, until you sweep a ship through it at a fifth of the speed of light. Every second, the front of that ship plows through 6 billion centimeters of road. Take a hull face a few meters across and multiply it out, and the bow is absorbing trillions upon trillions of atomic impacts every single second, each one arriving with the energy of accelerator radiation. The gentle haze has become a fire hose of particles, a continuous sandblasting delivered at nuclear energies. And it never lets up, not for 1 second of the 5-year crossing. Interstellar space never changed. The ship changed. At Voyager's pace, the vacuum is a silence. At Starshot's pace, the same vacuum is a wall of thin fire. And the ship spends the entire voyage flying face first into it. And the atoms are only the drizzle. The real weather is the dust, scattered through the space between the stars, vastly rarer than the gas. Our solid grain, flakes of carbon and rock cast off by old stars, most of them far smaller than the width of a human hair. Let me walk you through one encounter, one single grain, because this is the moment the whole chapter is built around. Somewhere along the course, the ship's path happens to cross one of the larger grains, a piece of stellar grit approaching the width of a hair, adrift in the dark for 100 million years. The ship arrives at 20% of the speed of light. No sensor sees the grain, because nothing that small can be seen at any useful distance. No pilot could react, because at this speed the last 1,000 miles of warning pass in a 50th of a second. There is no swerving, no braking, no lock. There is only the arithmetic of the baseball. Mass times the square of a terrible velocity. The grain meets the bow, and in a flash too brief for any instrument to follow, it delivers the energy of a hand grenade into a point the size of a pinprick. Metal does not dent at these energies. Metal vaporizes. A little crater blooms in the hull, edges melted glassy, a wound punched by something the ship never saw and never could have seen. One large grain, one grainard, and a light year of road is long enough to promise a supply of them, along with an endless rain of smaller cousins doing their quieter damage the whole way. The engineers who study flight at these speeds, including the Starshot teams, write it plainly in their published papers. Erosion from gas and dust is a certainty of the voyage, a design requirement, a weather forecast that reads 100%. Any ship that makes this trip makes it behind a shield, a thick sacrificial face of material at the bow, built to be vaporized, layer by layer, crater by crater, all the way across the light year, protecting the cargo behind it by dying slowly in front of it. So, we add the shield. Of course we add the shield. And I suspect you already hear the trap springing, because you have been listening all night. The shield is mass, tons of it, riding at the front of a ship whose every gram was already the most expensive gram in engineering. Heavier ship, bigger energy bill. At 7 Hiroshimas per kilogram, bigger bill. More fuel or more beam. More fuel means more mass. And the tyranny stirs in its sleep. And the new mass needs shielding of its own. But here is what I find genuinely strange about this chapter. stranger than the dust itself. The armor can absorb the grenades. That problem, at least, has a shape engineers recognize. Sacrifice enough material and the cargo survives. The deeper trouble is quieter and almost sounds like a riddle. Every impact, every vaporized crater, every particle strike across 5 years pours energy into the ship. The engine pours in more. The electronics pour in more. All of it becomes the same thing in the end. It becomes warmth in the walls. And on this ship, unlike every machine you have ever owned, that warmth has a terrible property. It cannot leave. Everything you own that works hard also sweats. Your car has a radiator up front drinking the wind. Your laptop has a fan that whirs up under load. Your own body sweats and flushes, shedding the heat of simply being alive into the air around you. This is so universal, so woven into every machine and every creature you have ever met, that you have probably never once said the rule out loud. Whatever burns energy makes heat, and the heat has to leave. And something has to carry it away. On Earth, something always does. The air takes it. The water takes it. The wind takes it. Every engine on this planet quietly leans on the atmosphere the way a runner leans on the breeze. And the atmosphere never sends a bill. Now step into space. And the first fact of the vacuum is that the breeze is gone. There is no air to blow across a radiator. No water to pump past a hot engine. No medium of any kind to accept the heat and carry it off. Every cooling method, your intuition knows. Blowing on it, dunking it, fanning it, standing it in the shade on a windy day. Every single one requires stuff around the hot object. And out there is no stuff, which produces one of the most backward-sounding truths in all of engineering. Space, the coldest place there is, a few degrees above absolute zero, is one of the hardest places in the universe to cool anything down. The cold is real, but the cold cannot reach you. Heat is a thing that must flow out of you, and there is nothing out there to hand it to. A ship in a vacuum keeping its heat is a thermos, the same physics that keeps your coffee hot all morning. A sealed container wrapped in nothingness now wraps the entire vehicle. And a thermos is a lovely thing, right up until you install a fusion engine inside it. There is exactly one exit, one loophole the universe permits, and you already know it, because you use it every time you feel sunlight on your face. Radiation. A hot object glows, sheds its heat as light, infrared mostly, and that glow needs no air, no water, no anything. It simply sails away into the dark. The sun heats your face across 93 million miles of hard vacuum through this one channel. So a starship cools itself the only way it can. It glows. Engineers build radiators. Great thin panels plumbed with hot fluid, spread wide to face the emptiness, and the panels shine their cargo of heat into the void. Every serious spacecraft flying today carries them. The space station's radiator wings are among the largest structures on it. And now, the trouble. In 3 short steps. Step 1. Radiation is a slow exit. Glowing is the weakest form of heat shedding there is. A trickle where a breeze is a river, which is why your thermos works in the first place. Step 2. The trickle must somehow drain an ocean. Add up what our test ship is generating. An engine channeling energy on the scale of national power grids. And even at superb efficiency. Waste heat measured in gigawatts. A bow absorbing a fire hose of particle strikes. Every impact becoming warmth in the armor. Electronics. Life support if anyone is aboard. All of it shedding heat. All day. Every day. For years. Step 3. The only faucet for draining that ocean is glow. And glow scales with surface area and temperature. Run the numbers for a gigawatt-class starship and, depending on how hot you dare to run the panels, the radiators required range from enormous fields of metal to something approaching square miles of it. Vast thin wings dwarfing the ship they serve, spread like the fins of some impossible deep-sea creature, shining dull red in the dark between the stars. You already know what those wings are made of. Mass. Enormous. Thin. Fragile mass. Exactly the kind that last chapter's dust storm loves to shred. And armoring them makes them heavier, and their weight swells the energy account at 7 Hiroshimas per kilogram. And the extra energy makes extra heat, which demands more wing, but set the spiral aside this time. Because with heat, the thing chasing the ship around that circle deserves to be named plainly. It is a bookkeeping rule. Energy in must equal energy out, or the inside gets hotter, forever, until something fails. A starship needs speed. Yes, it also needs to be a machine that can run a small nation's power grid inside a sealed thermos for years without cooking itself. The brochure never mentions the fever. The engine gets the applause. And somewhere behind it, always, the radiators do the surviving. So take stock of where the night stands, because we have come a long way from that innocent little division problem in the hook. The scoreboard still reads 5 years for a gram and roughly a decade for a fusion liner. And stacked behind those numbers now are the walls. The energy. 7 Hiroshimas a kilogram. The dust. A grenade in every large grain. The heat. An ocean draining through a glow. Every number on that board has been fighting for its life since chapter 11. And remarkably, the numbers are still standing. Let them enjoy the moment. Because now it is time, all the way back at the start of tonight. In the rules. I folded one final law into my pocket and refused to explain it. I told you it was the expensive one. I told you a ship would eventually get fast enough to break it. That ship has arrived. The fastest of the night. And the pocket is now empty. And the rule goes on the table. Every machine we have raced tonight. Every single one, from Voyager to the Starship, has been failing this test in the same hidden way. None of them was ever going to arrive. They were all going to miss. Here is the rule I have been keeping in my pocket since chapter 2. A journey does not end when you reach the destination. A journey ends when you stop at the destination. Say it out loud, and it sounds like nothing. Like a technicality. Like the fine print on a boarding pass. Now watch what it does to every number on our scoreboard. Go back to the Starship. The hero of the night. The 5-year machine. Follow it through its whole voyage one more time. And this time, keep your eyes open at the end. The launch. The beam. The sail riding a column of light. 20% of light speed in minutes. Then the long coast. 5 years of silent, falling through the dark. The fire hose of atoms. The grains. The little craft enduring all of it. And then, at last, the finish line, our invisible mark. 1 light year out, the ship crosses it, at 20% of the speed of light, and keeps going. There is no break on a starship. There was never going to be one. The engine is a mountaintop in Chile, 1 light year behind it, and a laser can only ever push, never pull. So the crossing is a flyby, and at this speed the word flyby barely covers it. If our finish line were a world instead of an empty mark, if there were a planet sitting there with oceans and weather and a surface worth a photograph, the chip would sweep past the entire planet in a fraction of a second. The whole destination, the object of 5 years of flight, experience for less time than a camera shutter stays open. One blurred glance, a handful of frantic snapshots radioed backward, and then the destination is behind it, shrinking, gone, while the chip sails on into nothing with all of its speed intact. Unstoppable, unsteerable, spent. That is what the 5 years on our scoreboard actually purchased. A bullet does not visit the target. We wrote that rule in Chapter 2. And then, like every headline ever printed about this subject, we spent the whole night forgetting it. And every popular number you have ever heard about interstellar travel forgets it the same way. Distance divided by speed. That is the calculation behind them all. And distance divided by speed is the arithmetic of a drive-by. It times the crossing of the line, with the speedometer pinned, and it says nothing at all about being there. Arriving is cheap. Staying is the expensive part. How expensive? This is where the night's whole education pays off. Because you already own every piece of the answer. Stopping means shedding speed. All of it. From 20% of light down to 0. And speed, Chapter 12 taught us, is energy. 7 Hiroshimas per kilogram at 1/10 of light. And that energy does not vanish on request. Every joule the engine spent making the ship fast must now be spent again. Unmaking it, slowing down, is speeding up. Performed in reverse. At full price, the bill for the journey was never 1 acceleration. It was always 2. So the ship must carry its brakes, and the brakes are an engine, and the engine needs fuel. And now listen carefully, because this is the cruelest sentence of the night. The exact place where the Tyranny closes its jaws. The braking fuel is cargo for the entire first half of the trip. Every ton of propellant reserved for the stop must first be accelerated to cruising speed along with the ship, hauled across the light year at 7 Hiroshimas per kilogram. All so it can be burned at the far end to cancel the very speed it was dragged up to. You pay to speed the brake fuel up. Then the brake fuel pays to slow you down. The costs multiply. One tank feeding on the other. And the rocket equation, which was merciless with 1 burn, becomes something close to unpayable with 2. A ship that must stop is many times harder than a ship that flies past. And every gram of that difficulty is charged at the front of the trip. Where mass costs the most, the engineers know all this. Of course. And the paper fleet has its paper answers. Magnetic sails. Vast loops of superconducting wire flung wide to drag against the thin interstellar wind. A parachute woven from a magnetic field, breaking against the light of a star waiting at the destination, using the target's own glow as a cushion. Clever, gorgeous, genuinely promising ideas. And every one of them shares 2 properties. None has ever flown, and all of them are slow. Gentle brakes that begin their work years early, trading away big slices of the cruise speed the scoreboard was so proud of. The honest summary is short. Stopping is an open problem with a wish list. So the scoreboard, our companion all night, gets rewritten under the full rules. And this is the quiet massacre of the evening. Voyager, 17,600 years. And give the old machine this much. It is the one contender whose number barely moves. Because at 38,000 miles an hour, the universe hardly notices whether you stop. Parker, still disqualified. Still on paper only. Orion. 100 years to cross the line. But an Orion that must break into a halt at the far end burns bombs at both ends of the voyage and arrives well beyond its century. Cargo slashed. Timeline swollen. Daedalus. And here the truth should be told plainly, because its own designers told it plainly. The 10 years was always a flyby figure. Daedalus was designed from the first page as a ship that does not stop. Its instruments built to do their science in a screaming pass measured in hours. Precisely because its engineers ran tonight's arithmetic back in the 1970s and understood that a breaking Daedalus was a Daedalus that could not exist. And the Starship, 5 years. Flyby only. Stamped in red. A number that was never for us twice over. Too small to carry a body. Too fast to ever be caught. Under the full rules of the test, the board is carnage. Every glamorous number of the night either bloats, breaks, or wears a red stamp. And yet, I promised you at the start that tonight had 3 true answers. And the third one, the strangest one, is still out there. A little over 2 years. That number is real, and it obeys every rule on the table. It starts at rest. It carries a payload. It arrives. And it stops. And here is the twist the last act of tonight turns on. The one thing that decides whether that number can exist has nothing to do with engines. Before the fastest ship of the night can make its run, the ship has to answer to its cargo. The final wall of this test is the passenger. And the passenger sets exactly one condition. It sounds humble, and it is going to design the entire vehicle. How hard can you push a human being? Every wall we have hit tonight belonged to physics or engineering, energy, dust, heat, brakes, hard walls, but honest ones, the kind you can attack with better machines and bigger budgets. The last wall is different, because the last wall is made of flesh. Somewhere inside the fastest ship of the night there is going to be a passenger. And the passenger is a creature of fluid and soft tissue that evolved for walking. And the passenger brings its own limit aboard. Strangely, the limit has nothing to do with speed. The body does not care about speed at all. And that single fact is about to save the whole night. The body's limit is on acceleration, on how fast the speed is allowed to change. So before the final ship rolls out, we need 5 minutes of honesty about the cargo. Start with what pushing does to a person. And the Starshot launch is the perfect horror story to open with. The chip took its beating at thousands of G, thousands of times the force of gravity, and shrugged, because a solid wafer has nothing inside it to slosh. You do. You are mostly water, a heart, a brain floating in fluid, blood that must climb to your head every second of your life, under high G. All of that plumbing fails at once. At 4 or 5 G. Sustained. Most untrained people black out, because the heart can no longer lift blood the suddenly enormous distance to the brain. Fighter pilots in full pressure suits, squeezing and grunting through maneuvers, hold 9G for seconds and pay for it in tunnel vision and burst capillaries. A human strapped to the Starship's launch, thousands of G in minutes, would simply not be a passenger anymore. The chip's on-ramp to 20% of light is closed to biology. Permanently. And no medicine will ever open it. The road is fine. The on-ramp is fatal. So the crewed ship must take a gentler on-ramp. And now the question becomes wonderfully specific. What is the most acceleration a human being can live with? Around the clock. For months and years. Eating and sleeping and staying sane under it the entire way. And the answer has been sitting in this room with you all night. It is holding you to your bed right now. 1. The pull of Earth itself, the exact force your body was built for. Tuned to across 4 billion years of evolution. Aboard a ship accelerating at a steady 1G. The floor presses up with the familiar weight of home. Coffee pours the way coffee pours in your kitchen. Muscles keep their load. Bones keep their work. The inner ear reads a completely ordinary world. In principle, and I say in principle because no crew has ever lived under thrust for years. A 1G ship sidesteps the medical problems of weightlessness entirely. By the simple trick of never being weightless, the ship becomes its own planet. Gravity, included free of charge, generated by nothing but the engine's steady push. It feels slow. That is the trap your intuition is walking into right now, and I want to spring it carefully, because the payoff is the whole final act. 1G is a gentle nudge, a parking lot pace, barely more than an elevator starting up. Here is what the nudge actually does. 1G adds about 22 miles per hour to your speed. Every second, second after second, without rest, without exception. Hold it for 1 minute and you are moving 1,300 miles per hour. Faster than a rifle bullet, while feeling nothing but your own weight. Hold it for 1 hour and you pass 80,000 miles per hour. More than double Voyager's lifetime cruising speed. Achieved before lunch on day 1. Hold it for a single day and you are past 1.8 million miles per hour. 4 times faster than the fastest machine our species has ever built at the bottom of its dive toward the sun. That is 1 day. The gentle push never feels like power because it is never violent. It is something better than violent. It is relentless. Every record set tonight by every machine in this race falls inside the first 24 hours. To a force no stronger than the one pinning your blanket down right now. And the ship we are describing keeps pushing after that first day. It pushes for weeks. It pushes for months. The arithmetic of patient, compounding, unspectacular gain. The same arithmetic that quietly builds fortunes and erodes mountains. Gets handed the throttle of a starship and told to keep it there. How fast does a year of 1G make you? I will let the final ship show you. Because the number bends physics itself, and because there is a detail waiting inside it. The spare key I handed you all the way back in Chapter 3. Light's own strange timekeeping that is finally about to open its door. Every rule from the start of the night stands. Start at rest. Carry a payload. Arrive. And stop. The last contender obeys all of it. It accelerates at exactly 1G to the halfway point of the course, swings around in the dark, and brakes at exactly 1G the rest of the way, arriving at our finish line at a dead halt. Crew standing comfortably on the deck the entire time. The fastest ship of the night is also the gentlest ride in it. Send it out. Midnight. The last contender leaves Earth. There is no violence in it. No chain of bombs. No mountaintop laser. No crushing wall of G-force. The engine lights. The ship eases forward at exactly 1G. And inside, the crew feels their weight settle toward the rear deck, which has just become the floor. That is the entire drama of the launch. A floor. From this moment on, the ship will do only one thing. Hold that gentle push without a single second of rest. And we are going to ride along and watch what relentless does to a light year. The first day, as we saw, buries every record in this race. 1.8 million miles per hour by the first midnight. And the crew has spent the day unpacking, By the end of the first week, the ship is moving at over 13 million miles per hour, about 2% of the speed of light. 7 days of gentle pushing, and it has already doubled the cruising pace of Project Orion, the ship that needed thousands of atomic bombs. By the end of the first month, it is nearing 8% of light speed, closing in on the pace that Daedalus needed an ocean liner of fusion pellets and years of burning to reach. 2 months in, it passes 16%. The bag of sugar in the hold now carries well past its 7 Hiroshimas, and nobody aboard feels a thing. The bill from Chapter 12 is being paid in full, in installments, every single second, and the engine simply keeps writing checks. By the 6-month mark, the ship is moving at nearly half the speed of light. The pace car itself is now only twice as fast as a machine that has never once pushed harder than a bedside elevator. And still it climbs, though the climbing turns strange from here, because physics starts leaning on the scale. The closer any ship gets to the speed of light, the harder each new mile per hour becomes to buy. So the speedometer creeps upward through the second half of the first year. 60%, 65, 70, each gain costing more than the last. Until, a little past the ship's first birthday, about 13 months by Earth's calendar, comes the strangest moment of the voyage. The one maneuver this ship performs all trip. The halfway point of the course, the engine goes quiet. For a few minutes. Weightlessness. Then the entire vessel swings end over end in the dark. A slow, deliberate somersault, until the engine faces forward, aimed at the finish line. It relights. The floor becomes the floor again. The weight returns. Identical. 1G. And nothing about life aboard changes at all. But everything about the journey has. The ship is falling forward while braking now, shedding 22 miles per hour of speed every second. And it will spend the entire second half of the voyage slowing down. Exactly as gentle, exactly as relentless. Seen from outside, it is one of the loveliest ideas in astronautics. The fastest vehicle ever conceived spends half of its journey with its engine pointed at the destination, arriving the way a feather arrives at a floor. Top speed, at that flip, comes out at about 3/4 of the speed of light. 75% of the pace car. And now the clocks. Because the clocks are the payoff of the night. The ship crosses our finish line, brakes to a dead halt. Every rule obeyed. Start at rest. Carry a crew. Arrive. And stop. Earth's calendar. Counting faithfully from launch night. Reads 2 years and about 2.5 months. Say it against the scoreboard. 17,600 years. 15 centuries on paper. 100 years. 10 years. Flyby only. 5. For a gram. Flyby only. And now, under the full rules, with human beings standing comfortably aboard, 2 years and change. The floor of this race was 1 year, set by light itself, untouchable forever. A crude ship, pushing no harder than Earth pushes you, comes within about 14 months of the pace car, and the ship's own clock tells it differently. Here is the spare key from Chapter 3. The strange timekeeping I asked you to hold all night. Finally turning in its lock, Einstein showed, and a century of experiments has confirmed to exquisite precision, that time runs at different rates for different travelers. Motion changes it. A clock moving fast through the universe genuinely runs slower than a clock at rest. measured every day in particle accelerators and in the satellites your phone is listening to right now. At everyday speeds, the effect hides past the 10th decimal place, which is why your life never shows it. At 3/4 of the speed of light, it steps out of the decimals and into the open. Aboard our ship, at cruise, clocks tick noticeably slower than Earth's. Hearts, too. Everything, evenly, together, so that no one aboard feels anything but an ordinary day. And when the ship stops at the line and the crew compares calendars with home, the arithmetic of the whole voyage lands like this. Earth aged 2 years and 2.5 months. The crew aged 1 year and about 11 months. Roughly 4 months of time. Real time. Simply did not happen for them. They arrive 4 months younger than their own mission calendar back home says they should be. And both calendars are correct. I will hold this door barely open, because tonight belongs to 1 light year and 1 light year only, but you deserve a single sentence through the crack. Keep a ship like this accelerating past our finish line. Hold the 1G for years instead of months. And that little 4-month gap grows without limit. Until entire centuries of Earth time can pass inside a single decade of ship time. The universe, it turns out, pays its fastest travelers in time itself. That is another night's story. Close the door, because this story has 1 turn left, and it is the turn the whole evening has been built to reach. Everything I just described obeys physics completely. The trajectory is textbook. The relativity is measured fact. The G-load is gentler than a staircase, which is exactly what the passenger demanded, and the passenger got every wish. So find the flaw. You have been trained all night for exactly this. So pause the tape in your head and ask the 4 questions. What does this engine burn? Where does the energy come from? At 7, Hiroshima's a kilogram, and far worse near the top. Paid twice. Once up and once down. What does the bow look like after plowing through interstellar dust at 3/4 of the speed of light? Where a large grain arrives with the force of artillery. And where? On a ship built for humans. Do the glowing radiator wings go? The 2 Year Starship has no answers. Not one. It is a trajectory. A flight plan drawn in ink so pure that no engine ever built or credibly designed can fly it. The passenger set the terms. 1G. 2 years. And physics accepted those terms without complaint. The energy account is what nobody can fill. For a crude vessel, accelerating and then braking. The total runs to a scale. No fusion design touches and no antimatter inventory will meet in 1,000 years of kettle boiling. Physics signs the permission slip. Gladly. In full. Physics was always willing. It is our hands that cannot pay. And the gap between those 2 signatures, between what the universe allows and what a workshop can build, is the exact width of the final answer to tonight's question. So come back with me now. 1 last walk to the finish line. The clock is still running, and it is time to read it out loud. The line is right where we left it, at the start of the night. 1 light year out, hanging in the dark, marking nothing. 1,000 stadiums of emptiness between here and there. The pace car crossed it long ago. At 1 year, exactly. A record that will outlive the stars, and scattered down the track behind it. Frozen mid-stride. Is everything the human race has ever flown, designed, or dared to put on paper. Walk the results with me. Slowly. 1 contender at a time. They have earned a slow reading. Voyager 1. The only contender actually on the course tonight. 50 years out. Faithful. and still in the first stadium's shadow. 17,600 years. The honest answer of everything we have truly built. Parker's solar probe. 1,560 years. Written in red. On paper only. The fastest object in human history. And every mile of that record borrowed from the sun and handed back on the climb. A diving speed. Never a traveling one. Orion. 100 years. Purchased with 4,000 atomic bombs and orphaned by a treaty the world was right to sign. The ship that physics approved and civilization declined. Daedalus. 10 years from a standing start. Flyby only. Designed at a London pub by engineers honest enough to print their own impossibilities. The finest starship ever drawn. Fueled from an industry at Jupiter that does not exist. And built, by its maker's own admission, never to stop. The Starship. 5 years. Flyby only. Payload 1 gram. The most astonishing number of the night. Real arithmetic on unbuilt engineering. And a door exactly 1 gram wide. An answer for a message. Never an answer for a messenger. And the 2 Year Starship. 2 years and 2.5 months by Earth's clock. 1 year and 11 months by its own. Crew at Earth wait the entire way. Arriving at a dead stop with every rule of the test obeyed. The only contender of the night that finishes the course as truly us. And the only one that exists nowhere at all. A flight plan without a machine. Permission granted by the universe. And unclaimable by our hands. So, how long would it actually take us to travel 1 light year? You now own the full answer. And the full answer comes in 3 layers. And every layer is true at once. With machines we have actually flown. The honest number is thousands of years. 17,600. By the only vehicle really out there running. With the boldest machine seriously on the drawing board. 5 years. For 1 gram. 1 way. No stopping. A postcard at 1/5 of the speed of light. And for human beings, for the us in tonight's question, physics itself quotes a shade over 2 years. Signed and sealed. And engineering cannot yet build the pen. The gap between those last 2 truths, between the permitted and the possible, is where the entire future of this subject lives. And notice, one last time, what the night actually taught. The distance was never the villain. 6 trillion miles is just road. And road is patient. The trouble was the price of hurry. Energy that squares as you climb. Dust that turns to artillery. Heat with 1 slow exit. A stop that costs as much as the start. Every year we tried to carve off the clock tonight. The universe priced. Precisely. And the price always climbed faster than the clock fell. 1 light year is not too far because light needs a year to cross it. It is too far because everything with mass must pay for every second it tries to save. Here is the picture I want to leave on your nightstand. The finish line is still out there right now. As real as anything unmarked can be. 1 light year from your pillow, in every direction you could point. And on the track, the whole entry list of our species comes down to 1 machine, a 1-ton spacecraft from 1977, 38,000 miles per hour. Gift speed from Jupiter, 17,500 years from the line and running anyway. It does not know the race is long. It does not know the race exists. It simply holds its pace through the dark. The slowest contender on the board and the only one that ever showed up. And there is something in that worth keeping. The paper fleet sleeps in its drawers. The old machine runs. If tonight rearrange the way you see that machine, or that sky. A like and a subscribe Genuinely help this channel keep making long nights like this one. But that can wait until morning. For now, turn off the screen and let the numbers settle where they landed. 1 year for light. 2 for the ship we cannot build. 18,000 for the one we did. Good night to you. And good night to the slowest runner on the track.